Good morning students. Good morning students. Today we have lecture number 7. Lecture number 7 on fluid mechanics. Lecture number 7 on fluid mechanics for first year. For first year. Okay. Okay. So far up to lecture number 6 we have studied about the fluid statics and fluid dynamics. We have discussed about the fluid statics and fluid dynamics. So today in this lecture number 7 we shall discuss about the viscosity. We shall discuss about the viscosity. Okay. About the fluids only. All the things are related to fluids. Okay. So now to maintain the motion of a liquid, an external force is required. That is, a liquid will flows when an external force is applied. A liquid will flows and external force is applied. So there will be a relative opposition in the layers of the liquid for the motion. And this opposition is because of a property of the liquid, and that property we call it as viscosity. So now let us understand what is viscosity. So viscosity, the property of the liquid due to which it opposes the relative motion between its different layers. The property of liquid due to which it opposes the relative motion between its different layers is called as viscosity. Viscosity, I am telling the definition of viscosity. The property of liquid due to which it opposes the relative motion between its different layers is called viscosity. And the force between the layers opposing the relative motion is called viscous force, and the force between the layers opposing the relative motion is called viscous force. Once again I will repeat. The property of the liquid due to which it opposes the relative motion between its different layers is called viscosity. And the force between the layers which opposes the relative motion is called viscous force. And this viscous force is also called as viscous drag. It is also called as viscous drag. Viscous force is also called as viscous drag or backward drag, or it is also called as backward drag. Okay. So now let us understand about this properly. Okay. So now consider the flow of liquid. Consider the steady flow of liquid over a horizontal stationary surface. Consider the steady flow of liquid over a horizontal stationary surface. This is a horizontal stationary surface. Let us consider this as a pipe. Otherwise, consider this as a pipe. Okay. Okay. This is a surface, lower surface of the pipe, and this is a upper surface of the pipe. Upper surface is not required. Okay, leave it. Okay. So now the steady flow of the liquid. Let us consider the steady flow of the liquid over the fixed horizontal layers. That is, there are different layers of liquid having a steady flow. These all are the layers of the liquid having a steady flow. Okay. We will consider a little bit far apart. Okay. As we move, okay, consider the steady flow of liquid over a fixed stationary surface, fixed stationary horizontal surface, over a horizontal fixed surface. These all are the layers of the liquid. Okay. As we move above the fixed surface, above the horizontal fixed surface, the velocity of the layers increases gradually. As we move above the fixed surface, the velocity of the layers increases gradually, and the topmost layer, the uppermost layer moves with higher velocity. The uppermost layer moves with maximum velocity. Velocity of this layer is maximum. Velocity of this layer is maximum, whereas the layer which is in contact with the fixed surface, the layer which is in contact with the fixed surface, the velocity of the layer which is in contact with the fixed surface is 0, is said to be at rest. The layer which is in contact with the fixed surface is said to be at rest, or velocity of this layer, velocity is 0. Velocity of the layer which is in contact with the fixed surface is 0. As we move above the fixed surface, the velocity of the layers increases gradually, and the topmost layer moves with maximum velocity, and the layer which is in contact with the fixed surface will have 0 velocity. Understood? So now consider two layers. Consider two layers. Okay, any two layers will take. Okay, consider two layers. These two layers. So let us say CD and MN. Consider two layers CD and MN. The layer CD is having a more velocity and the layer MN is having a less velocity. The layer CD, which is moving with a larger velocity, tries to accelerate the layer MN. The layer CD, moving with more velocity, larger velocity, tries to accelerate the layer MN. Whereas the layer MN, moving with less velocity, tries to retard the layer CD. Understood the retard? So the layer MN tries to retard the layer CD. As a result of this, a backward force, a dragging force exists between these two layers. A dragging force exists between these two layers in a direction opposite. A dragging force exists tangentially between these two layers in a opposite direction, and this force we called as viscous force. Understand properly. Consider two layers CD and MN. CD is having a more velocity because it is at a higher distance from the fixed surface, and MN is at a lower distance from the fixed surface, so it will have less velocity. And the layer CD tries to accelerate the layer MN, whereas the layer MN tries to retard the layer CD. As a result, a backward dragging and tangential force exists between these two layers. A backward dragging tangential force exists between these two liquid layers, and that force we called as viscous force. Thus, to maintain the uniform motion of the liquid, an external force is required. To maintain the uniform motion of the liquid, an external force is required. Understood? Okay. So now consider the steady flow of liquid over a horizontal fixed surface. Okay. So here the layers will slide these layers will slide over each other. They will not mix up. Remember that the layers of the liquid slide over each other and they will not mix up. That is, it is nothing but a laminar flow. It is a laminar flow of liquid. That is steady flow or laminar flow of liquid. In the laminar flow or steady flow, the layers of the liquid does not mix up. Understood? Okay. So now let us consider two layers CD and MN. Let the velocity of the CD layer is V plus dV. The velocity of the layer CD is V plus dV, and the velocity of the layer MN is V. And the distance of the layer CD from the fixed surface is x plus dx. The distance of the layer CD from the fixed surface is x plus dx, whereas the layer MN is at a distance x from the fixed surface. Consider two layers CD and MN having the velocity V plus dV and V, which are at a distance x plus dx and x respectively from the fixed surface. So now the dV by dx, the factor dV by dx is called rate of change of velocity with distance. The factor dV by dx is called rate of change of velocity with distance. That is, as the distance changes, the velocity will also changes. Because as we move upward, the velocity will be more. As we move downward, the velocity will be less. So as the distance changes, the velocity will changes. Understood? So it is the rate of change of velocity with distance. The rate of change of velocity with distance, and this is called velocity gradient, and it is called as velocity gradient. What is velocity gradient? If they ask what is velocity gradient, the rate of change of velocity with distance. The rate of change of velocity with distance is called as velocity gradient, and the unit of velocity gradient is per second. The unit of velocity gradient is per second. That is dv by dx. dv is nothing but change in velocity. It is meter per second, and dx is nothing but distance, meter cancel, so per second. Understood? The unit of velocity gradient is per second. Understood the velocity gradient? What is velocity gradient? The rate of change of velocity with distance is called velocity gradient. Now let us find the formula for viscous force. So according to Newton, the viscous force acting between the two layers of the liquid, the viscous force or the viscous drag acting between the two adjacent layers of the liquid. The viscous force acting between the two adjacent layers of the liquid is directly proportional to the area of the layers. According to the Newton, the viscous drag or the viscous force acting between the two adjacent layers of the liquid is directly proportional to the area of the layers and directly proportional to the velocity gradient between the two layers. The viscous force acting between the two layers of the liquid, the viscous force acting between the two different layers of the liquid is directly proportional to the area of the layers, and also it is directly proportional to the velocity gradient between the liquids, velocity gradient between the liquid layers. Thus we can write that is F is directly proportional to A and F is directly proportional to dV by dx. So now combining these two formula, so we can write F directly proportional to A dV by dx. F directly proportional to dV by dx. And now remove this proportionality sign and write a constant. So F is equal to a constant we have to write, and that constant I will write it as eta. That constant I will write it as eta. A dV by dx. A eta dV by dx. So this is the formula for viscous force acting between the two layers of the liquid. The viscous force acting between the two layers of the liquid is given by F is equal to minus eta A dV by dx, where A is the area of the layers and dV by dx is the velocity gradient between the layers. dV by dx is the velocity gradient between the layers, and eta is called proportionality constant. Eta is proportionality constant, and it is called as coefficient of viscosity. It is called as coefficient of viscosity. Eta is proportionality constant and it is called as coefficient of viscosity. What does the negative sign shows? Anybody? The negative sign shows that the viscous force or the viscous drag is in a direction opposite to the direction of motion of the liquid layers. The negative sign shows that the viscous force is in a direction opposite to the direction of the motion of the liquid layers. Understood? Okay. So this is according to Newton. So now if A is equal to 1, that is unit, and dV by dx is equal to 1 per second, that is unit velocity gradient. Then what happens? Then you can write F is equal to minus eta. F is equal to minus eta, or just eta is equal to F. Eta is equal to F. Now define coefficient of viscosity. Eta is called coefficient of viscosity. Now how to define coefficient of viscosity? See, when A is equal to 1 meter square, that is unit area, and dV by dx is 1, then F will be equal to eta. That is, you substitute there eta into 1 into 1. So F is equal to minus eta. So that is eta is equal to F. Now I will define the coefficient of viscosity. The coefficient of viscosity is defined as The coefficient of viscosity is defined as the viscous drag, viscous force acting per unit area of the layers. The coefficient of viscosity between the layers is defined as the coefficient of viscosity between the two layers is defined as the viscous force acting per unit area of the layers having a unit velocity gradient. The coefficient of viscosity is defined as the viscous force acting per unit area of the layers having a unit velocity gradient perpendicular to the flow of liquids. Once again, coefficient of viscosity is defined as the viscous force acting per unit area of the layers having a unit velocity gradient perpendicular to the direction of flow of liquid. Perpendicular to the direction of flow of liquid. Understood? So, this is the definition for coefficient of viscosity. Simple definition for coefficient of viscosity. So, coefficient of viscosity will be numerically equal to the viscous force acting between two layers. Viscous force per unit area between the two adjacent layers moving with a unit velocity gradient. That is also you can tell like that. Okay, understood? So, this is coefficient of viscosity and this is Newton's explanation on viscous force. So far you understood the Newton's explanation on viscous force. Newton's explanation on viscous force. Let us understand the units of coefficient of viscosity. Units of coefficient of viscosity. Okay. So, according to Newton, the viscous force is given by F is equal to minus eta A dV by dx. Okay. So, therefore, coefficient of viscosity eta is equal to F divided by A into dx by dv. This is the formula you can write. Okay. So, now in a CGS system, the unit of eta, that is unit of coefficient of viscosity, eta is equal to, in CGS system unit of force is dyne and unit of area is centimeter square, unit of distance is centimeter, unit of velocity is centimeter per second. Now centimeter cancel, so I will get dyne, this is per second goes to numerator, it becomes second, and centimeter square goes to numerator, it becomes per centimeter square. So dyne second per centimeter square, and in CGS system this the unit of coefficient of viscosity is poise. That is, in CGS system the unit of coefficient of viscosity is poise, and this is called as 1 poise. That is, 1 poise is equal to 1 dyne second per centimeter square. Now define 1 poise. Define 1 poise or unit poise. Define 1 poise or unit poise. The coefficient of viscosity of a liquid is said to be 1 poise. The coefficient of viscosity of liquid is said to be 1 poise if a tangential force of 1 dyne per centimeter square. If a tangential force of 1 dyne per centimeter square of the surface is required to maintain a relative velocity of 1 centimeter per second between two layers 1 centimeter apart. See here, I am making a definition for unit. Define 1 poise. The coefficient of viscosity of a liquid is said to be 1 poise. The coefficient of viscosity of a liquid is said to be 1 poise if a tangential viscous force of 1 dyne per centimeter square of the surface is required to maintain a relative velocity of 1 centimeter per second between two parallel layers 1 centimeter apart. Between two parallel layers of the liquid 1 centimeter apart. Understood? So define 1 poise. So 1 poise, that is, coefficient of viscosity of a liquid is said to be 1 poise if a tangential force of 1 dyne per centimeter square of the surface is required to maintain a relative velocity of 1 centimeter per second between two layers, between two parallel liquid layers 1 centimeter apart. So this is unit, CGS unit. This is CGS unit of coefficient of viscosity. So now in a SI system, the unit of coefficient of viscosity is decapoise. The unit of coefficient of viscosity is decapoise, or it is also called as Poisson. It is also called as Poisson. It is also called as Poisson. Okay. So now that is eta is equal to, so that is eta is equal to F. It is force in SI system. Force in SI system is Newton, and area in SI system is meter square, into distance in SI system is 1 meter, that is meter only. So velocity in SI system is meter per second. Meter cancel, so you will get, so how much you will get? This is 1 Newton second per meter square, 1 Newton second per meter square, and this is called as 1 decapoise. It is called as 1 decapoise. 1 decapoise or 1 Poisson. This is the SI unit of coefficient of viscosity. The SI unit of coefficient of viscosity is decapoise or Poisson, and 1 decapoise is equal to 1 Newton second per meter square. So now define 1 decapoise. Define 1 decapoise, or define 1 Poisson, or define SI unit of coefficient of viscosity. Like this they will may ask the question. The coefficient of viscosity of a liquid is said to be 1 decapoise. The coefficient of viscosity of a liquid is said to be 1 decapoise if a tangential force of 1 Newton per meter square of the surface. If a tangential force of 1 Newton per meter square of the surface is required to maintain a relative velocity of 1 meter per second between two layers of the liquid 1 meter apart, between two layers of the liquid 1 meter apart. Once again I will repeat. The coefficient of viscosity of a liquid is said to be 1 decapoise. The coefficient of viscosity of a liquid is said to be 1 decapoise if a tangential viscous force of 1 Newton per meter square is required. If a tangential force of 1 Newton per meter square of the surface is required to maintain a relative velocity of 1 meter per second between two layers, between two parallel liquid layers 1 meter apart. Understood? This is the definition for decapoise, or decapoise is also called as Poisson. It is also called as Poisson. Remember that the SI unit of coefficient of viscosity is Poisson, whereas CGS unit of coefficient of viscosity is Poisson. And now the relation between this decapoise and Poisson, that is 1 decapoise is equal to, directly I will write 1 decapoise is equal to 10 Poisson. Remember that 1 decapoise is equal to 10 Poisson, or 1 Poisson is equal to 10 Poisson. 1 Poisson is equal to 10 Poisson. Understood? Okay. And this 1 decapoise can also be written as 1 decapoise can also be written as Newton per meter square is nothing but Pascal second. 1 Pascal second. 1 decapoise is same as 1 Pascal second. 1 decapoise is same as 1 Pascal second. Pascal, Newton per meter square is nothing but unit of pressure, and unit of pressure is Pascal. Pascal second. Understood? So like this also you can define. So these all are about units of coefficient of viscosity. Understood? CGS unit, SI unit, and they will ask questions related to this one many times for 1 marks. So they have asked once what is the SI unit of coefficient of viscosity, and many of the students have written answer as Poisson. Many of the students written the answer as Poisson. So Poisson is correct or decapoise is correct? Decapoise is correct. Decapoise you have to write, or you have to write poisile, not poise. Poisile you have to write. Understood? So poise means that will be the CGS unit of coefficient of viscosity. Okay. So now the dimension of coefficient of viscosity. So dimension of coefficient of viscosity. So what are the dimension of coefficient of viscosity? So that is same formula. Use the formula eta is equal to F divided by A into dx divided by dv. So from this the dimension of eta, that is the dimension of coefficient of viscosity, is equal to dimension of force. Dimension of force is m l t raised to minus 2. You know, I think you know all these things. And dimension of area is L square into dimension of distance is L, and dimension of velocity is L t raised to minus 1. Now simplify this one. So now the dimension of m is only 1, m will remain. L raised to 1, and this is L raised to 2, and here also L raised to 1, and this L raised to 1, this L raised to 1 cancel. So this L raised to 2 taken to the numerator, L raised to minus 2. So 1 minus 2, L raised to minus 1. Understood? T raised to minus 2, and here T is T raised to minus 1. When this T raised to minus 1 goes to numerator, T raised to plus 1. T raised to minus 2, T raised to plus 1. That means T raised to minus 1. So this is the dimension of coefficient of viscosity. The dimension of coefficient of viscosity is m raised to 1, L raised to minus 1, and T raised to minus 1. Remember that. Understood? Okay. So now let us understand the effect of temperature on viscosity. Understood? These are the things. Okay. So next, effect of temperature. Effect of temperature on viscosity. Effect of temperature on viscosity. Okay. Effect of temperature on viscosity. Okay. First, viscosity of gas molecules. See here properly. Viscosity of gas molecules is due to the diffusion of gas molecules from one layer to another. Viscosity of gas is due to the diffusion of gas molecule from one layer to another. And as temperature increases, that is, as temperature increases, the rate of diffusion of gas molecules will also increases. As temperature increases, the rate of diffusion of gas molecule will also increases. So hence, the viscosity of the gas will increases. The viscosity of the gas will increases with increase in temperature. Viscosity of gas will increases with increase in temperature. Increases with increase in temperature. See here once again I will tell, understand properly. The viscosity of gas is due to the diffusion of gas molecules from one layer of liquid to another layer. From one layer of liquid to another, and the rate of diffusion of gas molecules increases. The rate of diffusion of gas molecules increases as the temperature increases. Hence, the viscosity of the gas will increases with increase in temperature. And for a gas you can write, for a gas, that is for a gas, the coefficient of viscosity of gas is directly proportional to the square root of temperature. You can write the coefficient of viscosity of gas is directly proportional to the square root of temperature. The coefficient of viscosity is directly proportional to the square root of temperature. Understood? So in the case of gases, the viscosity of the gases will increases. The viscosity of the gases will increases with increase in temperature, because because viscosity of the gas is due to the diffusion, and the rate of diffusion of gases will increases as the temperature increases, hence the viscosity of the gases will increases. Okay, second one, viscosity of liquid. Viscosity of liquid. The viscosity of liquid is due to the cohesive force between the molecules, among the molecules of the liquid. Viscosity of the liquid is due to the cohesive force among the molecules of the liquid. As the temperature increases, the kinetic energy of the liquid will increases. As temperature increases, the kinetic energy of the liquid will increases. As a result, the cohesive force between the molecules decreases. The cohesive force between the molecule decreases. Hence, the viscosity of the liquid will decreases. The viscosity of the liquid will decreases as the temperature increases. The viscosity of liquid will decreases. The viscosity of liquid decreases as temperature increases. See here, as temperature increases, the viscosity of the liquid will decreases. As temperature increases, the viscosity of the gas will increases. In the case of gas it is different, and in the case of liquid it will be different. Understand this. Once again I will tell, viscosity of liquid is due to the cohesive force among the molecules of the liquid. Due to the cohesive force among the molecules of the liquid, the property of viscosity is observed. Okay. So now, as the temperature increases, the kinetic energy of the gas molecule, the kinetic energy of the liquid molecules increases. Hence, the interatomic distance will increases. That is, the cohesive force becomes weaker. The cohesive force becomes weaker. That is, cohesive force decreases as the temperature increases. Hence, the viscosity of the liquid will decreases as temperature increases. Understood? And the variation of viscosity with temperature is given by, so a formula NT is equal to N naught divided by N plus alpha T plus beta T square. So this is formula for variation of coefficient of viscosity of a liquid, where eta T and eta naught are coefficient of viscosity of liquid at T degrees Celsius and 0 degrees Celsius. Eta T and eta naught are the coefficient of viscosity of the liquid at T degrees Celsius and 0 degrees Celsius, and alpha and beta are the constant. Alpha and beta are constant. Understood? So it's all things are not required. Just you remember this sentence. Viscosity of the liquid will decreases as temperature increases. Viscosity of liquid will decreases as temperature increases, whereas viscosity of the gases will increases with increase in temperature. Understood? Okay. Next point, effect of pressure. Effect of pressure. Okay. Effect of pressure. Effect of pressure on viscosity. Effect of pressure on viscosity. As pressure increases, the viscosity of the liquid will increases. As pressure increases, the viscosity of the liquid will increases, except for water. Except for water. See here. As pressure increases, the viscosity of the liquid will increases. Viscosity of all the liquids will increases except water. Except water. For water, as pressure increases, the viscosity of the water will decreases. Remember that. For only water, as pressure increases, the viscosity of the water will decreases. As pressure increases, the viscosity of all the liquids increases except water. Whereas, in the case of water, the viscosity will decreases as the pressure of water increases. As the pressure of water increases. Okay. And the viscosity of gaseous molecule, viscosity of gas is practically independent of pressure. The viscosity of gas is practically independent of pressure. That is, pressure has no effect on the viscosity of the gases. Pressure has no effect on the viscosity of the gases. Understood? So this is effect of pressure on viscosity. Understood? Effect of temperature on viscosity and effect of pressure on viscosity. Okay. So now we observe that the viscosity and the friction, that is in the first chapter, that is in the first part of the syllabus, in the laws of motion, you will study about a concept called friction. Hope you have studied, but I think you have not yet studied about the friction. So it will comes in the laws of motion. The friction between the two solid surfaces. The friction between the two solid surfaces, that will comes in the laws of motion. This viscosity and friction are similar. The viscosity and friction are similar, and there are similarities between viscosity and friction, as well as there are differences between viscosity and friction. Let us see the similarities. Similarities between viscosity and friction. Similarities between viscosity and friction. Okay. The viscosity and solid friction oppose the relative motion. Oppose the relative motion. That is, viscosity opposes the relative motion between two liquid layers. Viscosity opposes the relative motion between two liquid layers, whereas friction opposes the relative motion between two solid surfaces. Friction opposes the relative motion between two solid surfaces, whereas viscosity opposes the relative motion between two liquid layers. Understood? So it is both viscosity and solid friction oppose the relative velocity. Next one. Both this viscosity and friction comes into action or comes into play only when there is a relative motion between the layers. Only when there is a relative motion. So viscosity and solid friction exist. Viscosity and solid friction exist or comes into play only when there is a relative motion. Only when there is a relative motion. If the relative motion is not there, then there will not be viscosity or there will not be friction. Understood? So it is viscosity and friction comes into play when there is a relative motion. That is, viscosity comes into play when there is a relative motion between the two liquid layers, and friction comes into play when there is a relative motion between the two solid surfaces. Understood? And next point, similarities. I am telling about similarities between viscosity and friction. Next point, the viscosity and solid friction, that is solid friction, is due to the intermolecular interaction. The viscosity and solid friction both are due to the intermolecular interactions. So these all arise, that is the property of viscosity or the property of friction arises due to the intermolecular interactions. So these all are the some similarities between viscosity and friction. Understood? Viscosity and friction both oppose the relative motion, and both will arise or both will come into play only when there is a relative motion. And this viscosity and friction are due to the intermolecular interactions. Understood? And now dissimilarities or difference between viscosity. Difference between viscosity and friction. See here, you have not yet studied about the friction, that's why this looks like something different. So it is not something very much different. So if you understood about, if you have studied about the friction, the things will become very easy. So once you study about the friction, then once again see this video about the viscosity and friction, the relation, the comparison between viscosity and friction if you want. Okay. So now viscosity and friction, difference between viscosity and friction. See here, the viscosity, that is the viscosity is that is the viscous force between the two layers is directly proportional to the area of the layers, or viscosity depends upon the area of the layers. Viscosity depends on area of the layers, whereas friction between two solid surfaces, viscosity between two liquid layers depends on the area of the layers. The friction between two solid surfaces is independent of the area of the solid surfaces. The friction between two solid surfaces is independent of the area, independent of the area between the area of solid surfaces. Of area, independent of area of solid surfaces. So here once again I will repeat, the viscosity of liquid layers, the viscosity of two liquid layers depends on the area of the layers, depends on the area of the layers, whereas friction between the two solid surfaces is independent of the area. Next point, viscosity of liquid, viscosity of liquid is independent of normal reaction. Viscosity of two liquid layers is independent of normal reaction. Viscosity of two liquid layers is independent of normal reaction, whereas friction between the two solid surfaces depends, friction between two solid surfaces depends on a normal reaction, depends on a normal reaction. The friction between two solid surfaces depends on a normal reaction, whereas viscosity is independent of a normal reaction. So these all are the differences between viscosity and friction, just for your understanding. Understood? So these all are the difference between the viscosity and friction, and similarities between viscosity and friction. Understood? Okay. So now the next concept. Let us understand the next concept. Applications of viscosity. What are the uses? Applications of viscosity. Applications of viscosity. Applications of viscosity. Liquids of high viscosity are used, the liquids of high viscosity are used in shock absorbers and buffers of train, buffers in a train. That is shock absorbers. To make the shock absorbers of vehicles, the liquids of high viscosity are used. Liquids of high viscosity are used in making shock absorbers and buffers in a train. The viscosity of air and liquid is used in dampening the motion of instruments, dampening the motion of instrument. To dampen the motion of instrument, to dampen the motion of instrument, motion of instrument, the viscosity of air or liquid is used. To dampen the motion of instruments, to dampen the motion of instruments, that is machines, the viscosity of air or liquids are used, and the viscosity of the liquid will changes with temperature. Hence, by knowing the change, variation of viscosity of liquid with the temperature, a proper choice of lubricant is made in a proper season. In a particular season, the choice of lubricant can be made by having the knowledge of variation of viscosity with the temperature. That is, in the winter season, the viscosity of the liquid oil will changes. So in the winter season, we have to use a particular oil in the machines, in the vehicles, and in the summer season also the viscosity of the oil will changes. Hence we have to use a different oil in the summer season actually, but we will not use generally, but in the high level supercars, you know, so in such kind of machines, they will use different oils during the winter season, and they will use different oils in the summer season. Okay, so these are some applications of viscosity, and one more application is in the circulation of blood. Viscosity plays an important role in the circulation of blood. The circulation of blood can be understood by knowing the property of viscosity of blood. Understood? The viscosity of the blood is higher than the viscosity of water, little bit higher than the viscosity of water, and the viscosity of the blood will remain constant between the temperature 0 degrees Celsius to 37 degrees Celsius. Remember that the viscosity of the blood will remain constant between the temperature 0 degrees Celsius to 37 degrees Celsius. Okay. So these all are some applications of viscosity. Understood? Okay. So now next concept. Next concept we will study in the next classes. This much is enough for this class. Next concept, there is some more concept related to viscosity. We will study in the next class. Okay.